All right, I figured it out. I've got a proof. So, just to clarify what we're trying to prove. So, theorem. Given a string S, if S appears in the string S doubled with itself, without the endpoints, then S is a repetition of a substring of S. And I guess the way that I've worded this is not like mathematically rigorous, so the first thing I'm going to do in my proof is formulate it mathematically, but before we get to that, I want to sort of motivate this, because like, where would this possibly come from? So I guess the way that you should think about it is, let's suppose that S is ABC, ABC, ABC. Then you could imagine, like, one thing that you notice that you could do with this string is, like, if you took, so this is obviously just the characters ABC repeated 3 times. So if you were to take the first, like, chunk of that and move it to the end here, I'll use this vertical line to denote where the original string S ended. If you were to take this original chunk here and move it to the end, then you would have another copy of S just shifted over. And so one way to formulate this is that, like, if you were to take S plus S and just like concatenate it with itself, then what you would do is you would get ABC, ABC, then you would get another copy of ABC, ABC, ABC. And what you could do is you could have S like start here, so that you've got one copy of S here and one copy of S here, but then you've got another copy of S here which appears as a substring of the doubled copy of S. But not only does it appear as a substring, it appears as a substring not at the start and not at the end, because for any string, any string would appear if you included the endpoints, because you could just start at the very beginning or end at the very end. It's the fact that you get this S as a substring in the middle of S plus S that makes this special. And it's because you could take this chunk and move it to the end here. As you could imagine here, you'd take this chunk and you would move it here. So what this tells us is that if S is a so what we've shown here is that if S is a repetition of a substring of S, then S is contained in the interior of S plus S. And this fact is pretty straightforward. If you were given this fact and asked to prove it, it would be very straightforward, because you would just give this argument. So being able to see this is pretty straightforward. Now, the question is, do we have reverse cause? Does the reverse implication hold? So we know that if S is a repetition of a substring, then S is contained in the interior of S plus S. But is it also true in the reverse direction, that if S is contained in the interior of S plus S, then S is a repetition of a substring of itself? And that direction is what we need to prove to be true in order for the algorithm to be valid. And it turns out we can prove this to be true. It's just that this direction is a much more difficult task to prove it. Okay, and so before we get to that, I do want to take a moment to sort of like, let's think about this. Like I want to take a moment to like look at an example really quick to sort of build our intuition. This was really helpful for me for like wrapping my head around this problem and building some of the intuition. So let's say that we have a string S, which is A, B, C, D, E, F. Now, in this example, like I'm using these letters here not as literal characters in the string S, but as variables. So A is just the first character of S. B is the second character of S. C is the third. Oh, wait, we're in Python. A is the 0th character of S. B is the first character of S, etc. F is the 5th character of S when we start at 0. Okay, and so so in this context, these letters are not necessarily distinct. It could be the case that A equals B. It could be the case that A equals C, etc. Any equalities could possibly hold. But let's suppose it is the case that S is contained in the interior of itself, of the interior of twice itself. So it could be, what are the possibilities? Let's just write all of them out. So it could be, just to understand what I'm writing, it could be the case that S appears in itself, in the copied version of itself, just offset by 1. So you could write this string S here. And this would mean that this character is equal to this character is equal to this character, etc., etc. Okay. So what are all the possible offsets that could be true here? Let's keep writing them out. A, B, C, D, E, F. And finally, A, B, C, D, E, F. And the last one wouldn't count because then it would hit the endpoint, and that's not what we're looking for. We're only looking at these 5 interior cases. Okay, so what do these cases correspond to? Like, if it is the case that S is equal to, if it is the case that S appears just offset by 1 within S plus S, then that means that the character B equals A. So let's see here, the character A equals B, but then we also know that B equals C, and C equals D, D equals E, E equals F, F equals A equals B. So all of these characters are the same. So if this is the case, then S, so here we're going to say S plus S is just this. And if this is the case, meaning that S appears offset by 1 within S plus S, then S is just 6 copies of A, because in this case, all of the characters are equal to each other. Now, what about this case? In this case, we have A equals C, and C equals E, and E equals A. And that's it. So that's sort of like a cycle. And then we have B equals D, D equals F, F equals B. So that's also a cycle. So AB equals CD. AB equals, right? Yeah, AB equals CD. CD equals EF. EF equals AB. So what we actually have is we have S equals A, B, and then C equals A, and D equals B, and E equals A. I'm going to write this so that lines up. And then F equals B. Okay, so that's what it looks like in this case. In the third case, we have, let's see here, A equals D, D equals A, B equals E, E equals B, C equals F, C equals F. You might be seeing the pattern, but I'm going to keep writing it out anyways. Here it's ABC, ABC. In this case, we have A equals E, E equals C, C equals A. Then we have B equals F, F equals D, D equals B. So this is again A, B, A, B, A, B. Then finally here we have S again. It's just going to be okay. So what is the pattern that's emerging here? So here, let's say that I is the index that we're offsetting by. So here I equals 1, so we're offsetting by 1. Here I equals 2, we're offsetting by 2. I equals 3. Here I equals 4. Here I equals 5. And then what are these numbers over here? So here we have, let's see here, so we have all A's. So if we look at like the repeated character, we have A, we have AB, we have ABC, we have AB, and then we have A. So the pattern here is, let's see here, so ABC, so this is a sequence of length 3, and that's what I is equal to. And so let's see here. How many copies of ABC do we have? So I'm going to write the number of copies here. How many copies of ABC do we have? We have 2 copies. And no. The length of the repeated repeated substring is here. It's the length is 3. Here it's 2. Here it's 1. Here it's 2 equals 1. So these are the lengths of the repeated substrings. Now, what you can notice here is that there seems to be a pattern in terms of like how these numbers compare with the length of the string, which is 6. So 3, this is the greatest common divisor of 3 and 6, because 3 divides 6. 2 is the greatest common divisor of 2 and 6, because 2 divides 6. 2 is also the greatest common divisor of 4 and 6, because 2 divides 4 and 2 divides 6. I mean, obviously it's the greatest common divisor, because the only other integer you have there is 1, which is doesn't count. And then obviously 1 equals GCD of 1 and 6. It's also, well, it's not obvious, but I don't know. I don't like using the word obvious because it's easy to make people feel bad when you use that word in mathematics, and it comes up a lot. Anyways, so you might notice this pattern where it seems like the length of the repeated pattern, there's this relationship between the offset and the length of the pattern which is repeated. And it's that the greatest common divisor of the offset and the length of the string S is equal to the length of the repeated substring. And so this turns out to be true, and this can sort of point you in the direction of the proof. Okay, so I've spent a lot of time talking, and I haven't even started the proof yet. So let's start the proof. Okay, so so we are trying to prove, I think I mentioned that I was going to do this, but that if S is a substring of S plus S 1 through minus 1. Okay, so if there exists an index I, so saying that S appears in the interior of S doubled means that there is some index I that you can offset. Basically, S is equal to this. S is equal to S plus S starting at index I, where index I is some index which is greater than 0 because you can't start at the beginning, and it's less than the length of S because you can't end at the very end. So more explicitly, that if there exists an I such that S is equal to S plus S starting at index I, I should make these bounds explicit such that I is at least 1. Well, let's write it this way. I is greater than 0, and it's less than the length of s. And s is equal to s plus s. We start at index I, and we'll go all the way up to index I plus the length of s. Okay, and so here, like we can see just from this formula that if I were equal to the length of s, then this would go up to 2s, and so that would be the end of the string, and so that's why we have to stop at the length of s minus 1. Also keep in mind that we're using Python notation, so it's indices I up to I plus s minus 1. The last index of this string is I plus length of s minus 1. Okay, and that in and of itself is going to have the length of s indices, which is what you which checks out with the fact that s has to be equal to this. Okay, so if this statement is true, so this is the mathematical phrasing of the fact that of the statement that s appears in the interior of s doubled. Okay, so we are trying to prove that if this holds, then s is a repetition of a substring of itself. And we know that the substring has to start at the very beginning because that's just by the definition of it being a repetition of a substring. So then there exists a j, some index j, and j needs to be also, j needs to be in the same range, and we also need s to be equal to s. So it's going to be some multiple of s starting at the very beginning and going all the way up to j, index j. Yeah, where m is some integer here, and I guess the strictly like we don't really have to worry about the endpoints too much here because like s needs to be a strict substring. Okay, well I guess that's the only thing we need to make sure. We need to make sure that s is not a strict substring, and so that takes care of that. Okay, so and then for some natural number m, which is just like a yeah, for in this context, it's basically some positive integer. Actually, I'm going to write that because different people, whether or not the natural numbers include 0 or not, whether the natural number starts as 0 or 1 is actually a debate. It depends on mathematical. Different people use different conventions. Okay, but basically, point is the thing that we're trying to prove is that there is some index j such that s is just a substring from the beginning up to but not including index j repeated m times. Okay, so and in fact we're going to prove that j is the greatest common divisor of I and the length of s. Okay, so let's actually get started with the proof. Okay, so this is a problem statement. Okay. let, we're going to be using the length of s a lot. I've actually already used this a lot, so I probably should have done this already. We're going to let n be the length of s. We will first prove that basically, if you are taking the kth index of s, then you can shift by I, and you're going to get the same value. So remember, I is the shift of s within s doubled. So sk is going to be equal to s of k plus m times I mod n. And this is for any integer m. And let's see here. Here we have k. Okay. So really, what I should have done here is say that for all k, which is for every possible index of s. So every k which is between 0, any integer k between 0 and n minus 1, because these are the n indices of s. Okay, so to prove this, I actually want to, so where do I have this proven? Okay, I have this proven here. So I want to start with a, I want to start with a picture, because that will make this, the proof, because this actually makes a lot of sense once you see the motivation. But then, like, when you actually go to prove it, a lot gets sort of like jumbled up in notation, and it's easy to lose sight of the intuition. Okay, so let's just say we're going to give an example here. B, C, D, E, F. Okay, so this is where S is doubled, and well, here, let's just do this just to make it clear. Okay. So here we have I equals 4, because we're starting at 1, 2, 3, 4. Yeah, because we're starting at we start here, which is the 4th index of s plus s, because it's index 0, 1, 2, 3, 4. Okay, so I equals 4. And what we know here, what we see here is since, so s is equal to s plus s starting at index 4. So what that means is that a equals e, b equals f, a equals c, this, all of these things are equal. So this chunk is equal to this chunk, and this chunk is equal to this chunk. Okay, so ef, this chunk is equal to this chunk. But remember, so we have these two chunks here and here. But then we can move this over here, and we can move this over here. And so basically, what this means is that, like, we wait. Is this what I'm trying to prove here? Yeah, and so what this shows us is that if we take Okay, let me length of s minus I, s plus I. Okay, so let's start this, and we will see if what I wrote makes sense. So, and basically, okay, actually let's write this out. So what we're saying here is that like so we're saying S0 equals Si. So we have, we can basically break it up into these. So AB is S starting at 0 and going all the way up to N minus I. Because remember, N equals 6. So this is going to be, so this is AB. AB is S starting at index 0 and going up to index N minus Y, which is 2. And you don't include that index, so you just go up to 1. So it's in indices 0 and 1, so that's just AB. And so what we have here is that this is equal to, by the formula, we have this is equal to S plus S starting at I and going all the way up to, because what I'm doing is I'm basically using this formula. S equals S plus S, I all the way up to here. So if we take all the indices of S from 0 to N minus I, then we're taking all of these indices from I all the way up to, instead of ending, so here we would map N to I plus N. So if we're only going up to N minus I, then we are going up to I plus N minus I, yes. I plus S minus, I plus N minus I, which is just N. Okay. And note here, the reason that I'm, the useful thing about this is that like, so here, this is S plus S from I all the way up to N. So that's going to be, that's indices 4 and 5. So that's going to be, so these indices are all less than the length of S. So this is just S of I n, because the indices between S and S plus N are the same. Like S and S plus S are identical all the way up to index N. Because at index N, you have the second copy of S starting, and then S like just doesn't exist. And actually, really, this is Si all the way to the end. And this is really, actually, no, let's keep them. Let's just be explicit. We're doing a lot of math. Let's keep things explicit. So the so this vector S, or this substring S from 0 to N minus I is equal to Si all the way up to N. So this means Sk equals Sk plus I. And so if k is between 0 and strictly less than n minus I. Okay, so that takes care of that. And then, so that's what we know about AB. And basically what this says is that AB is equal to EF, or the substring AB is equal to the substring EF, which means that A equals E and B equals F. Okay, so now let's look at C, D, E, F here. And so here, what we have is we have S, and we have indices, let's see here, so C. this is index 3, so that's going to be 6 minus 4 plus 1. So no, it's index because it's 0, 1, 2, and that's equal to this. Okay, so it's n, and that makes no, it's I. Yeah. No, it's n minus I. Which, okay, and this makes perfect sense because this was a statement about indices up to but not including n minus I. So this should be a statement starting at n minus I and then going up to wherever C, D, E, F ends, which is the end of the string S. And I'm going to explicitly write that as n. Okay. So this is equal to, okay, so this part here, this appears in S plus S starting at A, B, C, D. So this starts at the beginning of S, actually. And so this, okay, so let's write that out. So this is S plus S starting at index n and going up to index n plus I. But because index n is where the second copy of S begins, this is just S starting from the very beginning and going up to I. Okay. And so now what does this tell us? This tells us that S of n minus k equals S of k if what? Okay. Let's see here, S minus k equals S of A. Do I have this right? I think I might be off by 1. N psi. Okay. 0 up to I, n minus I up to n. Okay, so this, so like for example, this is going to be, let's see here, so n minus, S of 0 is going to be equal to S of n minus I, S of 1 is going to be equal to S of n. Okay, because I'm getting confused, let's actually write this out. So S of n minus I equals S of 0. S of n minus I plus 1 equals S1. All the way up to what's going to be the very end. So S of n, no, we don't go up to n. We're going to get S of n minus 1 equals S of I minus 1. Okay, so S of k equals S of n minus I plus k if k is between 0. And what can k go up to? Well, actually, I think we want to do a substitution here. So instead of k, okay, we're running out of letters. L is not, let's use L. If L is between 0 and strictly less than I. Okay. And so then if we do like a substitution, I think what we want, because this is, okay, on the left we have a statement about 0 to n minus I. So here I think we want to start from n minus I and go from there. So if we were to start from, so if we wanted L to equal n minus I, no, we want this to start. Okay, I'm going to actually continue with the proof and see how this helps us. Okay, So let's prove that Sk k plus mi mod n for all m in Z. Okay. So we'll start with J. I mixed up notation in the video and my notes. So if k is strictly less than n minus I, then we have Sk is equal to Sk plus I. And why is that? That is this fact here. Okay. And now, what else do we have? So this is actually just going to be equal to S of k plus. Oh, well, I guess this isn't actually what I'm proving here, is it? Okay, I think I'm going to have to take a break and come back to this.